So meanwhile, others are joining in. Let's explain the plan for today. So today you have a 2-hour session. So the first hour will be taken by me to explain the concepts of your previous lessons. Then the next 1 hour will be utilized by Miss Ishani, I guess, for another exciting session on psychology. So we'll start the session within few minutes. And meanwhile, so the midterm exam will also be conducted in April. So up to now, the plan is to conduct the exams at the exam centers. So the time and the specific dates will be announced in due. So then what happens is you have to come to the relevant study center and do the exam under the exam center officers invigilation. Still people are joining in. Let's wait around 1 minute and we'll start the session. Okay, so I guess we should start without further delay. So now today we are going to discuss about the very important concepts regarding the number systems, which are the the core concepts of the digital systems, right? So you can't talk about digital systems without knowing about the number systems. So this session will be a kind of a summary of the previous content that I have uploaded into your LMS. So Now, if you can fully engage with this session and understand these concepts, so which is very important, because these fundamental concepts will be applied everywhere in digital systems. So first we'll look at the concept of number systems, right? So actually, what is a number system, right? So it's like a language, right, that we are using to communicate with each others, right? Now, let me take an example, right? So now I'm speaking English, right? And you all can understand me, right? So why that you all can understand me, right? What if I speak in another language? Let's assume that I'm going to speak in Japanese, right? Or maybe Spanish, right? Then what will happen, right? So then most probably you all can't understand me, right? So as I'm speaking in English, right? So you all can understand me, right? So what is the concept behind this? The thing is, we all are in a common agreement, right? So, or in layman language, we all have some knowledge about the English language, right? So we know what are the words that are used, right? What are the grammatical rules that we have to follow when using English? So we know somewhat about English, right? So therefore we can communicate with each other. So you can understand what I'm speaking here. But if I'm using Japanese or Spanish or whatever the other language, right, which you are not familiar with or you never learned, right? Or in other words, so you don't know what are the words, right? What are the grammatical rules, right? Or at least you don't know what are the letters used in Japanese or Spanish or whatever the other language, right? So therefore, we have to have some, common agreement when communicating day-to-day stuff, right? By using natural language, right? So in that case, right, we need to represent numerical values, right? Similarly, we need to represent numerical values as well in our day-to-day activities, right? So for an example, you need to go to a shop and you have to buy 1 kilo of sugar. So the numbers are involved, right? You are asking for 1 kilo. So the Mudalali will understand what is a 1 kilo, what is 1, right? Or maybe you are going to a fuel station and you ask for 4 liters of petrol, right? So the person who's providing the fuel, then he knows 4 is how much, right? So likewise, in our day-to-day activities, we need to represent values. So in that case, so when representing values also, or the numbers or the numerals, then again we have to have a systematic method, or a method that the both parties that communicating can understand, right? So then only we can have a proper communication and carry on with our work. So normally, so a number system, right, is a systematic method that we are using to represent values or the numerals, right? So in this world, there are different types of number systems, right? So we have positional or the weighted number systems, right? So we have weightless number systems, right? So we have, I mean, the systems that are not in the mainstream, right? Which only used by some group of people, right? Likewise. So to represent values, there are a lot of methods. So from the beginning of the civilization, people wanted to count. So they just wanted to know how many of stuff, right? Therefore, from the beginning of the civilization, people tried to count and keep track of their belongings, right? For an example, in ancient civilizations, so when people are like in the very early ages, when they are managing cattle, right? So they need to count how many cattle are there in my heap, right? Or maybe then they are cultivating lands, right? Crops, right? They need to measure, right? How much of or what is the area that I'm cultivating, right? So they need to count and keep track of information from the beginning of the civilization, right? So therefore, different types of number systems are there from the beginning of the civilization of the mankind. But when it becomes to the modern the information era, right? We have to particularly pick a best suit numbering system to work with our digital systems, right? Therefore, we are using the positional number system, right? Particularly the binary system, right? Therefore, before we learn about the binary system, we'll try to start from the place where we know, and we'll try to expand this concept, right? So we all can count like 1, 2, 3, 4, 5, 6, right? From the kindergarten or maybe the grade 1, right? So teachers are teaching how to count. So as we as a kid, so in those days, so we can count to 1 to 100. So we thought that we are the genius, right? We can count 1 to 100, right? Like 1, 2, 3, 4, 5, 6, 7, 8, right? So then in grade 4, 5, 6, right? Then we understood that no point of just counting, and counting never ends, right? Likewise, right? Can you remember that, right? In your kindergarten or the Montessori or the grade 1, right? How did you, I mean, practice this thing, counting, right? You just by heart, right? You just by heart 1, 2, 3, like you memorize that after 3 you have to say 4, After 4, you have to say 5. So you just by heart that. You never thought about the methodology of having these values in their line, right? Why number 1 comes first? Why number 2 comes after the number 1? Right? So we never thought about that. We just by heart, like parrots, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, likewise. So we never thought about why that happens or how that numbers are placed like that. We never thought about that. So actually, right, most of us are still don't worry about how the numbers are arranged like this. So this lesson is very important. So now we are going to learn how and why the numbers are represented in this manner, and then we will use the same concept to understand the binary system as well. Right? Okay. First of all, we will learn about the weighted number systems. Right? Later on, we can expand this to the unweighted and different type of number systems as well. So what we are doing is actually, right, when representing numbers, right? So we represent numbers with a radix or a base and set of digits, right? So let's try to solve this mystery, right? Okay. So let's do a simple activity, right? How many oranges are there? Right? How many oranges are there? So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? So very good. I'm getting some answers as well. Thank you. Right? So we all know that there are 15 oranges. Right? We have 15 oranges here. So I'm getting more and more answers. Thank you about that. Right? But how we counted like that? So what is the theory behind counting? Right? And if I say there are 15 oranges, right, you can understand how many of them. Right? So that is the basic requirement. We have to communicate how many, the value. Therefore, I can say, right, there are 15 oranges. How many oranges are there? 15 oranges. Or I can say, Pahaloi. Still, most of us can understand. We have 15 oranges. Or Dodamgedi Pahalawai. Still, the number of oranges are unchanged. Right? If we say 15 oranges or Pahalawai, we have only this much of oranges. Right? We have only this much of oranges. Or we can, in another language, we can say in Tamil, 15 oranges. I don't know the word for the orange, right? So still, we have this much of oranges. Even it is 15 Pahalavai or 15, right? The number of oranges still remains unchanged. Still we have 15. right? So therefore, now you have some idea that, right? So by using different methods, we can represent the value, right? I'm getting the, the name for the orange, totem palam, right? Thank you. And there are some Tamil words. I'm sorry, I can't read them. So the idea is, right, regardless of the language that we are using, we still have 15 oranges, right? So this is in natural language, right? So we can say this in Japanese, Spanish, French, or whatever the language, right? Still we have only 15 oranges, or this much of oranges, right? Now we'll try to expand this to the number system. So now what we can do is, we can write or represent the number of oranges like this, right? So we all can understand this number, right? So we know that this much of oranges are there. So we can understand, right? Or we can say we have 1 oranges are there. So if I say that in this picture we have 1 oranges, then this is not familiar to us, but still, right, this represent this much of oranges. Or I can say there are 17 oranges, right? Still, right, it represents this much of oranges. Or finally, we can say I have F oranges, or F number of oranges. Still, it represents this much of oranges. Right? Now we are in a trouble. We know 15, we know Pahalavai, we know Padinaindu, we know this 15 in numbers, but we are not familiar with 1111, 17, or F. Right? So the knowledge of number systems will tell us how to interpret these representations. Right? So why we know this is 15? Somebody told us this is 15. Maybe the English teacher at grade 3. Right? So our English teacher taught us, right, that this is the representation for the 15 in English. Right? Maybe the maybe our mother or father taught us that Pahalavai is this much of oranges or this much of stuff. Right? And maybe again, if you are from a Tamil speaking background, maybe again your mother or father may told you that this Padinaindu is this much of things, or it is 15. Right? And this representation is also familiar to us because maybe from the grade 1, right, we were trying to count 1 to 100. Right? So we, from the very beginning, we know that this is 15 and 15 is this much of things. It can be oranges, it can be money, it can be cars, whatever the stuff. right? But 15 is this, right? But still, we don't know how this 15 is formed like this. Why we are writing 15 with 1 and 5? So why we are writing these symbols, right? So let's try to understand why, right? Then we can identify how these numbers also represent 15. Or similarly, by using the same methodology, how can we represent values in different number systems, right? Okay, now let's try to understand this 15. Or we identify these representations like this. This is base 10 number system, right? This is base 10 number system. So this is base 2 number system. This is base 8 number system. And this is base 16 number system. Or you say decimal, binary, octal, hexadecimal, like English, Sinhala, Tamil. So we say base 10 or decimal system, base 2 or binary system, base 8 or octal system, base 16 or hexadecimal system. So that is the name that we are going to identify like English, Sinhala or Tamil, right? So by knowing or unintentionally, from the day one, we are familiar with the base 10 number system or the decimal number system. Therefore, first of all, we will learn how the decimal number system actually works. Then we can apply the same principle to the other number systems. Okay. So I'm taking this example from your slide, right? Now we have this value. So how can we read this value? So we all know that this is 9,240. Or in Sinhala, Namadas Desiya Hatalihai. I'm sorry, I can't say this in Tamil because I don't know Tamil. So if for a Japanese person, he will identify this thing as something else, right? So likewise, different people are having different understanding, but the value remain unchanged, like that 15 oranges, right? So then what happens is actually this representation is built like this, right? So from our right hand side, right, we can expand this representation like this. Right? So we can identify each digit or symbol like 0, 4, 2, 9, right? So we can identify these digits, and in our decimal system, each digit represents the positional value or the weighting factor, right? Or in grade 5 mathematics, we learned that this is units, right? This is tens, this is hundreds, and this is thousands. Right? But actually, what is the meaning of identifying that this is units, this is tens, this is hundreds, this is thousands, right? How the rightmost digit became the units, how the next position became tens, how the next position became hundreds. Did you ever thought about that? So we all learned that this is the units, this is the tens, this is the hundreds, and this is the thousands. But how they became units, tens, hundreds, and thousands, right? So how they became those weighting factors is because of the base. So sorry, right? Base of the number system. So we are using base 10 number system. Therefore, each positional value represents 10 to the powers. Right? As this is the base 10 number system, each positional value or a weighting factor represents 10 to the powers. Therefore, this should be 10 to the power zeros. This should be 10 to the power ones. This should be 10 to the power twos. This should be 10 to the power threes. So why 10 to the power? Because the base of this number system is 8. Right? So what is the meaning of this? Right? It is very simple, right? Base 10 means we are using 10 symbols, 10 digits to represent values. What are those 10 symbols? We identify this as 0. We identify this as 1. We identify this as 2. We identify this as 3, 4, 5, 6, 7, 8, 9. So altogether we have 10 symbols, right? Or we have 10 digits to represent values. Therefore, this is the base 10 system. On top of that, we have to place our weighting factors as 10 to the powers. If we are using 10 symbols, we have to go with 10 to the powers. Right? Therefore, when we are representing any value in decimal system, right? This is how values are formed of. This is how 9,240 is consist of. Right? Or simply, we have 0 units, 4 tens, 2 hundreds, 9 thousands. Altogether, we have this much of oranges, maybe, who knows, maybe money, whatever the physical thing. Right? So this is the mechanism or the principle that we are using in weighted number systems. So this explanation is particularly about the decimal system, right? So now we all know that how our day-to-day numbers are consists of, but we never thought about this, right? Maybe we know that these places or the digit represent units, tens, hundreds, and thousands, but still we never thought about why these positions represent those weighting factors, like why this is units, why this is tens, why this is hundred, thousands, likewise, right? Therefore, now we know the magic behind representing values in weighted number systems, right? So we can use same method, right, to represent values in digital systems as well. But because of several reasons, we are not using this system in digital systems, right? So most common system that we know as a digital system is our computer. So in our computers, we don't use this mechanism to, or this methodology to represent values based on some requirements. So later on, we will try to understand why we are not using this system. Before that, we will try to understand the binary system, right? So if it is binary system, right? So we have discussed that. So we have 10 symbols. So we can represent availability of each weighting factor by using these symbols in each positional value, right? Like this, right? So this is very systematic mechanism. So therefore we can represent any value, right? So we can expand this to the infinity. So there's no limit, right? In some numbering system, there are limits that you can represent values, but in this system, you can represent values up to the infinity, or it's going to never end, which means you can represent any value. So we just discussed that, but in modern digital systems, we are not using this decimal system. Instead, we are using binary system. Later on, we will understand why. So for the moment, we'll try to understand what is this binary system. Therefore, in binary system, the base or the radix is 2. Then there should be only 2 symbols. So earlier in decimal system, base is 10. Therefore, we had 10 symbols to represent values like this, right? But in binary system, the base is 2. Therefore, we can have only 2 digits. So we can freely choose any digits. So I will use box and a circle. I have 2 symbols. So I can name this is 0 and this is 1. Right? Or I can use whatever the symbols, like this is 0, this is 1. Right? Or this is 0, This is 1. Right? But when we are using this type of fancy symbols, which is very annoying to represent our values, right? Therefore, we are using the good old symbols 0 and 1, right? So we have only these two digits to represent values in our binary system. In binary system, base or the radix is 2. Therefore, we can have only two symbols. So we are using these two symbols. This represents 0. This represents 1. Right? If so, when we are representing values, right, our weighting factors should be in 2 to the powers. Earlier in decimal system, we had 10 to the powers. Now we have 2 to the powers. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, up to infinity. Again, you can represent any value by using binary number systems as well. Right? So shall we quickly go back the oranges, right? So if this representation is in binary, now we'll try to understand whether this is 15 or not. So we will place the values in our placeholders, right? Now, so 2 to the power 0 or units, right? 2 to the power 0 is 1. Therefore, we have 1, 1. 2 to the power 2 is 2. We have 1, 2's. Right? 2 to the power 2 is 4. We have 1, 4. 2 to the power 3 is 8. And we have 1, 8. So 8 plus 4, 12. 12 plus 2, 14. 14 plus 1 is 15. See, so this representation is also 15. Right? But we as humans, from the childhood, we are not using this system. Right? Therefore, by just looking at 1, 1, 1, 1, we can't quickly understand that this is 15 or this much of oranges. But as humans, we are using the decimal system from our childhood. By looking at this symbol, we can quickly understand this is 15 and 15 is this much of oranges. Right? So that's how the binary system works. Right? So nothing new, right? The similar methodology, the weighting factors are in 2 to the powers. Right? So in that case, in a proper representation, we have to always write down the base like this to mention that this is not the base 10 representation. But in practice, we don't do this. 15 base 10. Right? Why? Because as humans, we are using the base 10 system. Therefore, which is very annoying to have mentioning the base always. Therefore, only for the base 10 system, we are not going to represent the base like this. Right? But for all the other systems, we have to represent what is the base. So if this is in octal system, we have to mention the base. If this is in hexadecimal system, we have to mention the base. So can't you go for a base 3 number system? Yes, you can. Can't you go for a base 4 number system? Yes, you can. But in digital systems, the standard number systems that we encounter with are base 10 systems, base 8 system, sorry, base 2 system, base 8 system, and base 15 system. Right? So for an example, if we have a base 3 system, right, we can have 3 different symbols like 0, 1, 2. Therefore, if this base 3 system is utilized, we have 3 to the power zeros, 3 to the power ones, 3 to the power twos, 3 to the power threes, and up to infinity. Right? So if we have a value like 1, right? So the other thing is we don't read other number system values like 1111, 17. We don't pronounce them like that. So unless it is base 10, we have to pronounce it like 1111 base 2, 17 base 8, F base 16, or 1022 base 3. So if it is a base 3 number system, we can have 3 symbols like 0, 1, 2. Right? So the same principle applies. So if you grasp the principle, so all the number systems are just very easy for you. Right? So we'll try to understand what is the represented value here. Right? In this case, we have 2 3 to the power zeros. 3 to the power 0 is 1 or unit. We have 2 units, which is 2. 3 to the power 1 is 3. Right? 3 to the power 1 is 3, and we have 2 of them. So we have 6. We have 2 3 to the power 1s, or we have 2 3s. Right? 2 to the power 2 is 9. We don't have any 9s. 3 to the power 3 is 27. We have 127s. Right? So altogether 27 plus 0 plus 6 plus 2 is 35. So this representation is about 35 oranges, or maybe 35 rupees, 35 cars, right? Something about 35. Right? So what you have to do is to understand the representation, you have to quickly distribute or expand the representation into the positional values and their weighting factors. So how to identify the weighting factors? Weighting factors will be represented by the base. Right? So if it is base 2 number system, weighting factors goes like 2 to the power 0, 2 to the power 1, 2 to the power 2 likewise. If it is base 8 system, right? Eight to the power 0, 8 to the power 1, 8 to the power 2 likewise. If it is base 16 system, 16 to the power 0, 16 to the power 1, 16 to the power 2 likewise. So what you have to do, look at the base, right? Look at the positional values or the digits and add them up. So that's how you can represent different, the same identification in different number systems. So we'll quickly go through the octal system, right? So in octal system, we have 8 digits: 0, 1, 2, 3, 4, 5, 6, and 7. We have 8 digits, right? So this is the corresponding binary representation. So don't worry about that. Later on, we can identify the relationship in between different number systems. Right. Now we'll go back to the oranges. Right. Now this is in base 8 or the octal system. So will 1, 7 base 8 represents 15. Now we know. Let's find out. If the base is 8, we should have 8 to the power zeros, 8 to the power 1s, 8 to the power 2s, likewise. So in this representation, we have 7, 8 to the power zeros. We have 1, 8 to the power 1s. Right? And we don't have any other digits in this representation. Therefore, let's try to understand. 8 to the power 0 is 1. So we have 7 ones, which is 7. Right? So mathematically, right, any number to the power 0 is 1, right? So this is something we learned at school, right? Therefore, always the rightmost position will be units, right? So 8 to the power 1 is 8, right? We have 1 8s, right? So 8 plus 7 is 15. So this representation is also this much of oranges. Right. So finally, we look at the hexadecimal. Right. So in this case, we have a lot of symbols. We have 16 symbols starting from 0 and ending by F, right? Because we don't have single numbers to represent 10, 11, 12. Therefore, we are using English alphabetic characters. Right. So in hexadecimal system, A represents 10. In hexadecimal system, B represents 11. In hexadecimal system, C represents 12, D represents 13, E represents 14, F represents 15. Right. Therefore, let's go back to the orange for one last time. Right. If this is the hexadecimal representation or base 16 representation, right? The weighting factors should go from 16 to the powers, 16 to the power 0, 16 to the power 1, 16 to the power 2, likewise. So in this representation, right, we have only one digit, right? We don't have any stuff here. Therefore, let's try to understand this. So we have F number of 16 to the power zeros. We already know that any number to the power 0 is 1. So this should be units, right? We have F number of units, or we just understood that F is 15 in hexadecimal system. Therefore, we have 1 15s. Right? Or this is 1 times F, which means 1 times 50, because F denotes 15. So we have 15 and we don't have any other numerals. Therefore, this representation is also talking about this much of oranges, or 15 oranges. Right? Okay. So then we will, in next session, we will look at the relationships in between different numbering systems. How can we convert, and how can we use binary system in digital systems, especially with logic gates, to develop some binary systems. Right? So I think this is the end of today's session. So in next session, we will try to expand this and go one step further. I think Asmir is here.
Yes, I'm here.
Okay, great. So I will hand over the session to you, Dr. Asmir. Thank you.
Okay, thank you very much, Serena. I was listening to the binary session. I suppose I also learned a thing or two. So, girls and boys,